Hello and welcome to my today's video where I'm going to present you our wireless MBus to narrowband IoT converter and how it can be configured using our backend service. We are going to practically go through all the steps which are necessary to register the unit on our backend. Then we will register different meters. We have heat cost allocator here from Kundis Q-Caloric 5.5, and we also have a water meter from Madalena, and this one is a lactosonic water meter. And here of course is our wireless MBus to narrowband IoT unit, and of course a battery. And for monitoring what's happening with the device, I have connected a serial line so that we can practically see what is happening in the device. This is normally, of course, not connected in deployment because, well, you would not need the narrowband IoT in that case. Okay, so first to really quickly introduce how this works. So this device is wirelessly gathering wireless MBus frames from the meters, and then these frames are transmitted using narrowband IoT to Myotic, which is a SIM card provider, and this service is then forwarding the data to our backend. So I will very quickly show you what Myotic is. So in case you are in some of these countries, you can just buy SIM card from them, contact us, and we can create you an account in our backend, and then we can together do all the readout. In case you don't want to use Myotic, this is also possible. Our backend also works over UDP. In that case, we just need to create an open VPN connection between our backend and your server or backend, and then it can be or your private APN, and it can be used over UDP as well. But for simplicity, let's now consider you are using Myotic SIM card. So first of all, I will try to explain how the whole configuration process and data gathering process works, or how the messages are exchanged. And later on we will have a very quick practical hands-on. So as you can see on the screen I'm showing, at our wiki, new generation wiki, you can find an article about this device, which is quite long. It contains really definition of the whole application level protocol which is there between the hardware unit and the backend. The protocol is completely open, so it's up to you whether you will write your own backend service, or if you want to go faster, you can use the backend we have prepared. And of course you can also just buy the hardware unit and implement your own protocol. You can even use a transparent AT command, a function which enables you to directly communicate with the narrowband IoT module and use other protocols such as lightweight machine-to-machine, or any other protocol which is supported by the SIM7022 modem from Simco, which we have inside. So, but for now we will just stick to our protocol, which is fully documented here. And I will try to explain how this works. So first, when the device is booted, I will skip the part where the device sends so-called bootloader request. This is the very first message which is sent by a special part of the firmware which asks the backend whether there is a new firmware for the unit. The firmware update process is documented in a separate video on our YouTube channel, so if you just search the YouTube channel, and I will also put a link in the description, you will see how this process can be done. But for now, let's say that there is no firmware update and the device boots. In the Lua script, and what happens next. So next, the device sends a so-called beacon message. The beacon message is sent periodically. Normally it is something like once per 12 hours or once per day, and this beacon message contains some information like battery voltage, signal level, and some status information about the unit. If there is a pending configuration for the device, the server realizes that there is such a situation and sends a configuration down to the device using the 0x02 command. As answer, the device acknowledges the configuration by sending it back as is, and the server verifies that the configuration is correct. This configuration contains configuration of what wireless mode should be used for the readout, whether it is wireless MBus T1, wireless MBus S1, C1 is done together with T1. So if you select T1, you automatically also look for data in the C1. We also support protocol from Apator Metra. We support protocol from Sensus, Bubble Up protocol, and we also support Sontex, Radian protocol, but it is used on Sontex devices mainly. So all these configuration, timing on how long each mode should be used is sent to the device, and the device acknowledges that. Next, the IDs needs to be set up, and these are like either wireless MBus IDs or some other protocol IDs, IDs of the meters. In our case, these are the numbers which are here. So for the heat cost locator is 95794144, and for the water meter it's written down here, and I don't think you can see it, but it is 210114 Okay, so this is sent to the device, and the device doesn't send the whole list because the size of the uplink is limited for narrowband IoT to 512 bytes, and if the S1 ID is 4 bytes, this would limit us in the number of ID you can set up in the device. Currently, as the script is written, the limitation is 240 devices for one readout unit. In practice, we meet situations where we have something ranging from 100 to 200 devices or end meters per one readout unit. This is related to the environment where you install the device, and also to the range of our readout unit, which is, I would say, not bad. So, but of course, if you write your own logic in the Lua script, you can read out arbitrarily any number of devices by our readout unit. So, but let's get back to the process. So the server, the device acknowledges the IDs by sending a checksum of all the IDs, and then the server changes the state of the unit to a configured state. For the Sontex meters, the settings is a little bit different. There is a special list for setting the Sontex devices readout, because the readout is what we call it not passive. Our device is not just listening for the IDs, but it has to actively send a request to the meter. It has to transmit and then receive the answer. So I will not go into detail for this because this is a little bit specific. Then for Bubble Up protocol, for checking the integrity of the message, the key has to be set. If no key is set, then the default key is used, which is and default key is used quite often in the installations, so very often we don't need to do that for Bubble Up protocol. Okay, and now we are getting to the different gathering modes. What I was talking about until now is mainly what we call a multi-mode readout manner, or the way how to gather the data. Why we call it multi-mode? Because it supports multiple modes, and it is the mode to go for if you plan to integrate our backend, because with that mode you set the actual list of devices to read out. You also register the meters into our backend. You assign different parsers for the data which are read out for each meter, and like this, the best advantage is that the device knows when the readout is complete and it can stop the readout, so you don't need to waste the battery by reading, for example, for 1 hour or for some specific time, but instead you read only the IDs which are required to be read out. The inconvenience is that, of course, you need to provision the unit. You need to tell the unit what IDs, what meter IDs should it gather. Otherwise, it will not know what to do, and it will only send beacons and wait for the configuration. So this is first approach. Second approach is so-called send once script. It's available under a link here, and if you write this script into our wireless MBus NB-IoT hardware, what you can do, you can use no backend at all, and inside of the script you can, for example, set up that it should only gather last 3 days in a month, that it should only gather on work days, and that it should start the gathering process at 10 o'clock in the morning with some randomization spread. You can imagine if you have thousands of units starting the gathering process and all sending the data at once, it can non-uniformly load your server. So this load spreading is done also by setting this variable, and that's all you need to do. So yeah, what you can also do, of course, you define in what mode the readout should happen, but that's all you need to do. You don't need to set the list of IDs, because what the unit does in this case, it for every readout, for every wake up cycle, it gathers everything it hears in its vicinity, but only once, and then after a certain time it goes to sleep, and then it wakes up, and the whole process repeats. Okay, here is a little diagram explaining the situation. So we have either the pre-configured wireless MBus IDs, which is the multi-mode script, or we have a send once approach. And to make it even a little bit more complicated, but it's not for just to make it complex, but there's a reason for that, of course. There is for each of these strategies, there is either periodic readout, so you tell the unit wake up every 24 hours, but there is no synchronization involved. So if your meters are not transmitting like 24 hours per day, this is not the way to go. So we set a periodic readout as a backup, but there is also a scheduled readout which can be scheduled by the server. How this works? This is shown on the next diagram, actually, so I will use the diagram. As I said, the device is sending from time to time, once per day, this beacon message, and when the server realizes that there should be planned gathering, it answers the device with the message starting with the hexadecimal 0B, and it provides settings for how long and when, after what waiting time, it should start gathering. The device goes to sleep for that time, and then it starts gathering exactly at the time which it was requested by the server. So the server is governing the whole process. It tells exactly when the gathering or the meter's reception should start, and of course the device then reads all the meters, sends the report, at the end, and then the server acknowledges and the device goes to sleep. And then next time when another beacon is sent, if the server wants, he can trigger this. I'm always, when designing something, I'm always thinking of what will happen if this thing gets broken. And I was thinking, what happens if, for some reason, the downlink, the downstream, gets broken? Because, well, Narrowband IoT is with us already for some time, and as I said, there is a lot of companies involved sending and resending the data, etc. And there is the downstream and the upstream. If the downstream goes broken for some reason, and I set a periodic readout for once per week, for example, until the things get fixed, the device will trigger the readout by itself once per week if no plant gathering is scheduled by the server. So this helps us to overcome this period of Narrowband IoT infrastructure malfunctioning, for example. I know it's not really, maybe you can say it's not realistic it will happen, but I have seen a lot of things happening, so it's better be prepared. Yeah, so here is how we as I mentioned, there is the passive gathering and there is active gathering. Passive gathering is used for wireless MBus, Apator, sensors, bubble up, and etc. And active gathering is used for the Radian protocol on Sontex devices, which is a little bit different. The frames which are sent are a little bit different. You can go through this diagram by yourself, and you can also check the documentation of each command to really fully understand how this works together. But the principle is that first the passive gathering is done, and then the active if there is some Sontex device set configured in our readout unit. Okay, there is also something we distinguish between gathering and scan. Scan is not the same as gathering. Scan is used when you want just to have a list of IDs which can be seen from our readout unit, and you want to know the RSSI, but you are not interested in the data. You are just interested in the complete list of IDs which are reachable by our unit. And in that case, what the unit does, it scans for all available meters. Then it aggregates the information in one big frame or a series of frames, and then this is sent to the server. How this is used? If there are multiple devices like this, and you have a list of meters to be read out from, I don't know, a street, what can be done on the server? There is a so-called allocation which happens, and the allocation distributes the meters dynamically. Dynamically allocates the meters to the readout units in a way that each readout unit gets the meters it hears the best, so that we maximize the probability of readout on every cycle. So this is what can be done with our backend. Okay, I think such a high-level explanation of what will happen is okay, and now let's get to the practical part. So this is our backend. This is blueprint for API, which is generated by Swagger UI. So first let's authorize. So we will have the password, we will have username, we authorize. Of course, what this blueprint does, it from the website sends a post and get and other HTTP method requests to the server, and it uses the bearer token which was obtained by clicking on to this authorization. So now we are authorized. Well, this part is mainly for firmware and Lua script updates, but I will, for example, list the units. I have listed the units. I can see that there are so far there are no units registered for user with the name tester01. So what I will do now, I will register the first unit. I have already pre-filled this before. So this is the IMSI of our device. This is the device type. This is the default value which is there. Here you define what modes should be used. There are more modes, but this is to be extended. The default, we are by default showing just the S mode, T and C mode together, and the Metra mode. Okay, so here, as I know that we have T1 devices, I will set 240 seconds. Because what happens is that during the readout, the device is alternating between different modes, and as I wanted to do the readout only in T mode, I can put here any number, but up to, for example, 240. Time per device in seconds. What this means is how many seconds of scanning should be done for every ID which is registered for this given unit. An interesting thing is this interframe timeout. I will quickly explain what it is, and it can save quite a lot of battery actually. Let's imagine you have, for example, 100 meters out there connected to a single readout unit, and you realize that on average the whole readout process takes, for example, approximately 20 minutes, which is something which maybe I would expect in some cases. It depends of course on the period with which the meters send data, but it's 20 minutes is something I have seen. So what can happen is that 1 meter out of these 100 meters dies, the battery dies, for example, 1 watt meter is out. And if I would simply have just a single global timeout, and I would say, okay, grant up to 4 minutes of gathering, of receiving for each meter, this would give us something like 400 minutes of reception. But we know statistically that if there is no new meter received during, for example, 5 minutes, we know that it is very unlikely that anything new will be received. So this interframe timeout says that if we haven't yet reached the global timeout of the reception, but there is nothing new being received for 5 minutes in a row, then let's just give up and let's just send the final report of the readout, and what was not received until now will not be very likely received. So there is no point in keeping the reception. Yeah, so this is not really a timeout, but a different kind of timeout. Yeah, it's not the timeout from the beginning of the readout cycle, but it's a timeout checking the time between the last received meter and the current moment. Okay, here is the settings of the plant gathering. For simplicity, I don't use plant gathering in this demo, so I set days to sample to 0. What happens is that here the list of events where the readouts will be scheduled is then generated here. We don't use contact gathering, and these other settings is for MBus, wired MBus devices. Here, wake up period, I set here 3 minutes so that we can see it happening during the demo. Normally you would put here something like 1 day or something like that. Here is the list of IDs I want to read out. You can see it on the boxes. And and this is also important, this is the list of endpoints where the data should be posted. I have created a webhook site. If you go to webhook, if you put webhook site into Google, you will find this really nice project. We are running this on our testing virtual private server as well. What it does is when you load it without this suffix, it will generate you a unique URL, and then if you post the data to this URL, the data will be received here. There is some internal limitation, like it will I think delete the link after some time, etc. But for testing of some API, it's really nice, and it will visualize the data here as well. And it is nice and quick. So I have set the URL here, and anytime this final report message, I will quickly show. Yeah, this F4. Anytime this F4 the gather report message is received, what the server will do, it will generate a big JSON out of all gathered data. It will also, if a parser is set for the meter, or if there is a default parser set here, either the parser or the default parser is run on top of the data, and the data are also parsed before being sent. If you set all the parsers to empty string, then no parsing happens, and the data are sent over in raw format. If you want the parsing to happen, and if you have encrypted data, then you of course need to provision us with the keys. We understand in some cases you don't want to do that. In that case, you simply don't set the parsers, and you let the backend forward only the raw data. So it's up to you if you want to parse the data at the backend and use the backend as some kind of data unification point where you normalize the data so that it's always sent in the same format to, for example, your front end, where you only consume it and then visualize it to your customers, and you generate your own reports there. Or if you want simply us to forward the raw data and you take care of all this, it's up to you. We will support you in both cases. So okay, so this is I'm emphasizing this because our philosophy is really you either buy the hardware, you write your own Lua script, or you implement our protocol, or you integrate our backend, or you integrate it just partly as you wish, really. To further develop, if you don't want to do your own backend, what is also possible, we have an internal microservice called Wireless MBus Forwarder, and what it can do here, basically we don't put an external URL but a link to our forwarder, and we are able to generate for you daily or monthly reports to your email in Excel format, or we can upload this report to your FTP server over FTP, FTPS, or SFTP. This is something which is ready. So if you want to test it in this way, you can tell us, and we can set up the endpoint in a way that it is forwarded like that. And as you can see, this is not a scalar, it is an array. So what we can also do, we can make it being forwarded to your backend, forwarded to a webhook site, and we can also forward it, for example, to our forwarder service, which will generate the reports to your email. So anytime the gathering report is sent by this hardware, the backend can do all these steps so that you have the data in multiple formats if you want to evaluate it, for example. And then you of course switch maybe to one way to do things. Okay, so I think I've said enough, and I can finally click on the execute button. So let's execute it, and success. Yeah, so you can see the request here, the curl. This is the curl you would run from some of your automation script if you would like to automatically generate multiple devices. So you would do it this way, or if you want to integrate this backend with your backend, etc. So the unit is registered, and as you can see, I have already put here the IDs of the meters. I will register the meters. Well, it's not necessary to register the meters, but if I want to do parsing of the data as well, I need to register them. So here is the parser ID, wireless MBus meters. It is possible to define your own custom parser in Python and register it here in our backend, but there's really a lot of things which can be done in the backend, but we don't have time to really go through all of these, so I at least mentioned them. So here is the ID, ID of the 1 meter, execute, ID of the other meter, execute, and they are so I think wireless MBus, okay, and they are now both registered. I hope I did it right. You can always list it. Okay, I didn't register the other one because I misspelled the parser. We didn't check the result, yeah. Okay, and now they are both registered. What I will do next is I will go to this is user management. We don't need that. I will go to unit/log, and here we can this is in UTC. This is like a time filter. We can list the messages which were exchanged between the hardware unit and our backend. And as you can see on this right side, I have a serial console connected there. So what I will do now, I will finally plug in the battery, and this is a completely blank unit, and we will see what will happen. So the device is booting. You don't see a portion of the printout, but that's not important. Okay, and now we can either wait for it to boot. That's one option. It will receive, if there is no pending update, the backend sends it a message so that it boots directly. Or what I can also do, I can hold this this button and skip it, but maybe it will be better just to leave it as is so that it boots by itself. Okay, it received a 4B, which is a boot command. Now it is in the application part of the firmware, which is updatable. The bootloader is also updatable. There is a special firmware for that, which manages the update of the updater. So the whole firmware is entirely updatable. And now what the device will do, it will send F0FF, which is the beacon message, and you can see here, this is the bootloader request. We told him to boot, and here is the beacon. If I refresh again, I can see that we further send him the 02 command to configure him, and he acknowledged that, and then we send this. For some reason this is inverse, maybe the timestamps are too close. There is a pipeline for processing of the history, so but you can see the order here. This is the serial line output. Okay, and now I think the device will start the gathering, or maybe it will go to sleep and then wait for the wake up period and then start gathering. I'm not sure, but you can see these two IDs being added into the internal list of IDs. Okay, so it went to sleep, and after 120 seconds it will start gathering. If you press the button at this moment, the device wakes up, but if you wake it up using the button, it will not do what is scheduled next, but instead it will send a beacon message. This is for testing purpose, so if there is for a period of, I don't know, 1 day, and you go to some device and you just want to test if it's alive, you can click the button and you are sure it will not anyhow alter the gathering timing. It will only send a beacon message, and it will go back to sleep and wait for the specific time until the deadline is hit, and then only then the gathering will start. Okay, we have the webhook site ready where the data will be posted, and if I check the history of the exchange messages, we can see there is another beacon. An interesting, I will use the time, so an interesting function is also that you can switch this output type to parsed, and if you hit execute, you can have JSON explanation for every message. So here are explanation of what is sent in the beacon message, and you can see like what was the configuration which was sent, which was received, and everything can be parsed from that. But I will switch back to hex because, well, it's readable for me because I know the protocol by heart. It's not readable for normal user, but if we only look at the beginning bytes, you will understand approximately what's happening. Okay, and the device now woke up and it starts gathering in T1 mode. So now we just wait. Okay, so it received 1 node out of 2. And because there is a really nice feature which is further saving the battery, we don't send the narrowband message for every received frame, but the data are aggregated together if the maximum transmission unit of 512 bytes allows it. So this way we reduce the number of narrowband IoT messages which have to be sent, and this way we reduce the battery consumption. Okay, so what happened here, we send the data, then we send the report, and then the server acknowledged that. So I will check the history, and we can see here that it was actually received. And then if we go into webhook site, we can see that already the data were posted there, and we can see here that this is the raw data in base 64, a unit which did the readout, meter ID, and okay, I didn't select the right parser, because this parser only showed us like the ID timestamp out of the device and such things, but it doesn't matter. What I can do, I can manually copy this payload. I can go back. This can happen to you, that you don't select the right parser and you receive the data like that. Either you wait for the next readout cycle, you change the settings, you swear a little bit, or what you can do, you can go to parsers and you can test manually the parser. So you can go here, and if I copy the message here and I click on execute, it will give me the data. And here there is it's not very interesting because the hit cost allocator only has a 0 value on it, but maybe let's check the other guy, which is the water meter. This will be more interesting. And as you can see, you can always use either base 64 or hex. So we have the data in base 64, so we use this button, and we have 2.081 cubic meters. We have some flags, error flags, and there is also consumption at specific date, which is the end of last month. So to have a proof, I will approach the device to the, you can see 2.081 on the display of the device. So we got the readout right. It is posted here. You can imagine this is your backend, for example, and because the period is 3 minutes, the device will start the gathering cycle again. I think the period of transmission of this hit cost allocator is higher. Here I set up using NFC from Madalena, the application I set up the period of 47 seconds, so I think we are inside of the period inside the period of gathering here. But when I was testing this before turning this video, I missed this Q-caloric several times. This was to demonstrate the interframe timeout. So if we wait for 5 minutes and we are lucky enough, or if I smash this so that I prevent it from transmitting, we can see that the interframe timeout will happen 5 minutes after reception of this from this timestamp, yeah, not from this one. He just says he received again number one. Number one is the water meter in this case. Number two is and again is the heat cost allocator. You can see that it's approximately 47 seconds or so if we subtract it. I think it was some number like that. You can fold each part of the API so that it's not so overwhelming like this, and you can unfold only the part which is interesting for you. We are also working on a front-end service which will allow you to more easily set up things. This is not, of course, meant to be used by the end user. This is meant to be used by software. Yeah, it's an API. But well, if the installation is simple enough, it can be also used as a basic user interface to set up things. Okay, so we need to wait I think several more seconds, and we should get the interframe timeout, because if I'm right, we set it to we set it to this is the info. There is another endpoint called config, and this contains the configuration which is there, and I think it was 5 minutes. Yeah, so we should be hitting very soon these 5 minutes. Yeah, it is not exactly 5 minutes. It is always the radio is started and stopped for every received frame, so with some internal timeout, so it can be plus or minus 1 or 2 minutes, but we should be very close to the timeout now. Okay. Oh no, we were too lucky. So just before hitting the timeout, we received the other meter. Found all. Yeah, you can see this found all, which means I found it all. I terminate the readout and I send the result. Never mind. You can test it yourself, and you can see the interframe timeout. But you have the idea, right? So I explained during the video. Okay, so that would be. If you need to know details, do not hesitate to contact support@acrios.com or go through this document, and we will be happy for feedback. Thank you for watching, and see you next time.